All right, circuit satisfiability. How are we doing for time? We have another 2 minutes. We will not finish this topic in 23 minutes. But maybe. I talk fast. Will you understand it in 23 minutes?
No. Maybe talk fast, we won't get it.
All right, circuit satisfiability. What is it? You all know what a circuit is. It's AND or NOT gates. They could have 2 wires. They could have many wires. Let's say there's one output, right? And they have many wires coming in, and you feed in true, false, yes, no, 0, 1, high voltage, low voltage, right? You feed it in, and the AND or NOT trickles down, and you get an answer, right? And so an assignment says it satisfies the circuit if it outputs true. So this is a satisfying assignment because it outputs true, right? Given a circuit, can you find a satisfying assignment, or even know whether it exists? You could try all assignments, but there are too many of them, right? Is there a faster algorithm? We don't think so. All right, so here, when you're trying to do a reduction, the first thing to do, in fact, when you're trying to do anything in life, the first thing to know is what is the nature of each piece. You know, give a label to things. And I know that's probably why we have problems in life, is we want to label things. And that brings up whole things like racism and stuff. But that aside, we want to label things. What is that? That's our input. What's our input, right? What's our instance? It's a circuit. What's our solution? It's an assignment to the circuit, right? When is it valid? The assignment is valid if it satisfies the circuit, right? Is there a polytime algorithm such that given the circuit and given an assignment to the circuit, you can see whether it satisfies it? Yes, I give you a circuit, I give you an assignment, you put the assignment through the circuit and see if the answer is yes or no. You can do that in polytime, right? That makes SAT an NP, right? Right, goal, given a circuit, find a solution or know whether it exists, right? And so this problem, the circuit satisfiability problem, is a problem is the set of yes instances, right? So this is the set of circuits where the circuit is satisfiable. And you'll note that it's an NP problem because it's a yes instance if there exists a solution to it that you can check. Right? All right, the airplane problem, what is it? The input tells you what you want about the airplane. The solution tells you how to build it. Valid, given what you want for the plane and the solution how to build it, valid will tell you whether or not it's a good solution. Right? Yes, no. Yes, it's a valid solution. No, it's not a valid solution. Right? Goal, given the description of an airplane, you figure out how to build it or whether you can build it. Right? All right, so here, what is the problem? It's the set of airplanes that are buildable. When are they buildable? When there exists a way to build them. If you have a way to build it, you can test it. Yes?
Say, for example, if you're doing like a reduction of this and have the oracle for the plane problem.
Yeah.
Would the oracle say, yes, there is a plane that exists given the parameter, or would it give you the actual parameter of the plane?
Well, that's kind of what we were saying, the difference between an oracle and a fairy godmother. Oracles are only required to say yes or no. Right? Let's have polite oracles where if the answer is yes, they give you a solution. But they don't need to. And the truth is, if you have an oracle that you can ask over and over and over again, and then you can find a solution. Because you can ask, is there a solution? Is there a coloring of this graph where this node is red? Is there a coloring of the graph where this node and this node is red and blue and green? Right? So then you can do a binary search and you can find the solution. But let's not worry about it. Yes?
Does the fairy godmother search for valid, or does it search for the solution to the plane?
Given an input here, we want to know, does it have a solution?
Right. So what does the fairy godmother search for?
That's what I'm answering you. You have to let me finish. The solution, the fairy godmother gives me the solution. If it's a yes, if my instance is a yes instance, then there exists the solution where valid says yes, it's a yes instance. Right? So, in fact, here I'm going to do the entire Cook reduction. Just think of valid as a circuit. Right? And I'm asking, is there an S which will make this say yes? Right? That's what we're going to do. Let's do our reduction. What is valid? I said it was an algorithm, right? What's an algorithm? Turing says an algorithm is a Turing machine. Java programmers say an algorithm is a Java program, right? People who build circuits say that an algorithm is a circuit, right? We know that you can take any Turing machine and convert it into Java, and we know that you can implement those Java in circuits. Why do we know that? Oops, because that's what this is. It's a circuit, right? So we can take this algorithm and turn it into a circuit, all right? And then, how do we do a reduction? Here's the circuit satisfiability problem. We want to prove it's harder than the airplane problem, right? We want to prove it's harder than every NP problem. We want to prove if we could solve circuit sat, we can solve every problem that free lunch that the industry wants, right? How do we do that? Well, they're not likely to be in polytime, right? So we do a contradiction. Assume that we have an algorithm for the circuit problem, right? And then we're going to come up with an algorithm for the plane problem. Circuit, yes. The NP complete problems, the complete problems are the hardest ones for that class. You can have computable complete. You can have any polynomial complete. Any class has complete problems for it. Means if you can solve it, you can solve everybody in the class. Means it's the hardest in the class. All right? So this is just what we're doing before, right? All right, so let's do it. We're going to do our mapping, our instance map. We're going to map airplanes over to circuits, right? So here, let's do it. Here we have an algorithm for SAT. All right, so what does this guy give us? He gives us the requirements for an airplane, right? And we have to give him, our oracle, a circuit, right? So let's build a circuit. First, what do we want? We want a circuit. And what is this circuit going to compute? It's going to compute this. What is this? This is valid, right? Valid takes two inputs. It takes an instance. This is a valid for the airplane problem, right? We take the valid for the airplane problem, and we turn it into a circuit. So now the circuit for valid has two inputs. It has the input I as an input, but we know what I is. Right? Our boss gave us I. So we hardwire I in. What do we not know? We do not know the solution. What do we want to know up here? Is there a valid solution for I? What is that? Is there a way to satisfy this circuit? Right? Our oracle tells us, is there a way to satisfy the circuit? And if she's nice, she tells us, if she's a fairy godmother, she tells us the solution. Right? And what do we do with this? What is this solution? This solution is something that if you plug in here, out comes yes. So what is it? It's solving our airplane problem. Right? Everybody get that? Cook got a $300,000 a year job because he did this as a teenager. Right? Yes? As much as well, first off, let's clarify something. I have never been able to get my grad students to do a really good NP completeness reduction after spending weeks on it. So you are not going to have to do one on the exam. So that's the first step. Where are you going to have to do reductions? You are going to have to do one more reduction in your life on the exam, and that will be reducing to the halting problem. Right? it will look similar to what was on the test 3, and you will have to say something similar to what's on test 3. Does that answer your question?
Yeah, I just wanted to know if we were going to draw any sense maps, or not draw, but like code.
We are going to do one now. We have how many minutes? 12 minutes. In 12 minutes, I'm going to